All right, so welcome back, and welcome to this second modulus of this sort of, say, fundamental overview of some tools, which are actually instrumental for what we are going to see this afternoon and let's say, in the last 2 days of the course. So before starting, I will ask questions like Miguel, but I would say I will go much on the easy way. How many of you know how to calculate a spectrogram? Raise your hands. It's not valid, just say, I type spectrogram in MATLAB. Huh? Okay, so quite some people. You can use Google, okay? If it takes more than 5 minutes, then maybe it's better to listen here. And how many of you already surf on Wavelets? Okay, there are some users. All right, if you raise the hand twice, then you can sleep tight for the next hour. Well, hopefully you will not snore too loud. Otherwise, let's take this trip, and I will try to be more operative. So say, I will open MATLAB, so in case you have MATLAB, you can open it, at least the first code, I'll try to type it so that you can follow and try to get the same results on your screen. So let's say the starting point is the Fourier transform. We saw it already with Miguel. You have, say, the continuous transform in the discrete form. Actually, so this is a Fourier series, and that's basically what you're doing is changing the base. So you take your signal, you transform it into a different base, which is a whole bunch of sines and cosines with different frequencies, so say harmonically related. And interpretation as just a change of base is quite trivial. If you look especially for the discrete form, you have a signal that is discrete, is made of n samples. You transform it into some other n numbers that are complex, okay, and are the coefficients of this expansion. Well, I'm not going to be exhaustive, of course, but there are examples of applications that are huge and that say are all over the place. Just to give you a few of them that might be more interesting for us, one that made it very popular for fluid mechanics is transforming the PDEs in ODEs. This is the basic example, or you take the 1D heat equation, and you see that, say, you take an equation is a partial derivatives, so you apply the Fourier transform in space, so imagine you have an infinitely long bar, and then you obtain that since, say, in the Fourier space, the derivative is just a multiplication of the frequency, then you obtain an ordinary differential equation, which is much easier to handle. Filtering data, I guess you're all familiar. You take data that have some noise, like this blue curve, you apply a filter, and then if you have a nice separation between, say, the frequencies of your data and what the noise is, which is typically wide in most of the experimental application, then you can obtain a beautiful filtering of your data. Or compression, you take an image, then you pass it to the Fourier domain, and then, say, in most cases, images are smooth, say, they have long features, long regions where features are actually not varying much, like in this image, and so you can actually chop the reconstruction, you just retain the strongest coefficients, and you'll end up with an image which is actually beautifully resembling the original one, in this case with just 0.5% of the coefficients. This was actually quite an easy image to filter. So in the end, say, this is practically the cornerstone of a lot of engineering applications. So ranging from communication, every time you make a phone call, you're actually passing through something that uses the Fourier transform in some way, okay? So some elaborated form of Fourier transform to compress your data and make the transfer easier, as well as in computational physics, in CFD, use spectral methods to solve the Navier-Stokes, and advanced data analysis. And the key feature, let's say, what really made the big change is the FFT algorithm. So you have a very efficient algorithm which scales very well with large amount of data. You know that this operation here involves n squared operations. If you use the algorithm by Cooley and Turkey, introduced in 1965, you actually need n times the logarithm of n, which scales much more gently with the number of samples. And then, let's say, for continuous stuff, say sinusoids is actually quite a gentle basis where you can decompose your signal. So like in the image, for example, you have, say, smooth features, you can easily reconstruct it using sums of, say, continuous sinusoids. The problem starts when you have stuff that has information, frequency content that is varying along the signal. And the problem is that if you look at the formulation, in both cases, you're actually using, to determine your FT expansion, you're actually using the entire sequence. So let's say here you see you have a time integration, and here, for each coefficient, you're actually using all samples of the sequence, which means that you're giving up the time information to get something that is in different domain, that is that of the frequency. There are, of course, several cases where frequency changes over time, and it's interesting to look at that. One example is, for instance, if you think of music, and actually, let me go. This is a spectrogram representation of a piano concert of Beethoven, and what you see here is, in the vertical direction, we're actually going to do it, is the power spectral density of the music that is playing. So you see that the frequency content is actually changing over time, and it might be important in some cases to localize the feature where they're actually occurring. Or just another trivial example is heartbeats. So these are the data. This is actually a built-in example of MATLAB. These are data from the Kobe Heartbeat of 1995. And you see here that if you look at this sequence, there's actually, say, quite a long time where this is practically noise. There's very little activity there. And then you see that there is one spot where you start having, for like 3-4 minutes, more or less, some activity. Then there is another period is quiet. And then you have another spot with large fluctuations. Whoops. That was Heartbeat. Let's see. I made the system crash. That's awesome. It's rehearsing. Let's see. This just restarted. I don't know why. Let's see it again. See? Something happened here. I don't know what's going on. Sì. Aspetta. Sì. Yeah. Sì. Due secondi riparte, rapido. There you go. Okay. So too much shaking, maybe. Let's get back to this. So apart from earthquakes, of course, you can easily imagine that you might be interested to know where some event with a certain scale is occurring. Finance, for example, in the stock market, you want to know when a certain stock item is experiencing some resistance or some support or is making some fluctuations. In biology, for example, the electrocardiogram is a beautiful example where you want to filter out information. You know that what you're measuring is actually voltage differences outside of the body, so they're very weak, and the electrocardiogram is contaminated, for instance, by the 60 hertz of the light that is incoming. So you want to filter out, but at the same time, you also want to retain information about arrhythmias, for example. Okay, so you don't want to get a full sequence, say, okay, your heartbeat is whatever, 100 pulses per minute. You want to know whether there are various variations over time. And of course, if you think about turbulence, we know that it is multi-scale, but actually it's very interesting to see whether you can catch, if a certain scale that is active, where it is occurring. I mean, the spectrum is interesting, but it's even more interesting knowing where the actual scale is located. So how do you handle that? Well, if you think for a moment to the electrocardiogram, to the earthquake, what is the workaround, the easy one? Well, what you can do is to take this signal and you split it. Okay? So if you want to localize, just make it shorter in time. It's a very simple workaround, and then for all these sequences, you calculate the corresponding spectrum, and you identify that in that second window, for example, you start seeing some peak there, okay? So say around 50 millihertz, and then say you have in the last one, you have two peaks, which are two different activities. Of course, here you pay a price. The price is that the shorter the sequence, the less is your frequency resolution. So you have troubles in looking at the stuff that is occurring at, say, the large wavelengths, the low frequency of the spectrum. So this is the price to pay. And apart from that, such a, let's say, such a trick actually has an even larger price, that is that of basically what you're doing is windowing your signal with a boxcar function, which is as long as the window you're selecting, and then actually, you know, that introduces ripples in your spectrum. So you might want to do something more gentle, and that is at the basis of the Gabor transform. So what you do is practically, let's say, change your kernel of the Fourier function with a window. This window is sliding all over the signal, okay? And say one of the popular kinds of windows that you can use, and this is actually the one introduced by Gabor, is a Gaussian function. So what you're doing is replacing your sinusoids, which were going all over the domain forever and ever. You're actually replacing with Gaussians that are modulated. So they look like waves that are actually reaching a maximum and then decreasing with the Gaussian. So, for example, imagine that you have a signal like this one. It's a signal where you have two well-localized frequencies. You have two sinusoids, and you want to know locally the frequency content. Then what you can do is to pre-multiply the signal by this window. You make it slide, so you make shifting along the whole signal, and then locally what you get out, and this is actually not, let's say, an accidental choice, what you get out is that the sinusoid actually, let's say the function forming this expansion will actually look like this. They look like waves that are sort of smoothing to create a time localization of your spectrum. And then you can keep going. You can move the window all over the signal. And what you can do is to create a representation where you take all the spectra, you pile them up as columns, and say for each time, you put all one close to the other, and you get something similar to what we saw with the Beethoven piano concert. So say, for instance, these two would be something like this, okay? So in order to do that, we can try to do it in MATLAB. So if you have MATLAB now, you can open it, and you can try to follow what I do. So basically, first operation, we clean the environment. I don't know, you don't see it. That's annoying. That's annoying because I have to code over there. It's duplicated now. Well, okay, so we can use actually right away the code here. Okay? So first of all, what we do is to generate the signal. I'm taking a sequence that is, say, 2 pi of length with 2,000 samples, okay? I generate my spaced samples, and I select two frequencies. One is 3 hertz, the other one is 10 hertz. And then there is a parameter that I have to select that I partly overlooked before when describing the Gabor transform, is the standard deviation. Yes? Is zoom it in? Okay. Actually, what we can do is to go here. These are in the folder anyway, okay? Better now? Perfect. Okay, great. So what I actually overlooked before is the standard deviation. Evidently, when you make your windowing, you need to select how big is your window. So whether it is a sharp one or it is a large one. So here I've set like something like 0.5, which is the same that you find on the slides. And then what I do, well, first of all, I generate the signal. Okay, so it's just the sum of the two sinusoids, and putting here this Boolean here is just say switching on and off a sinusoid in a certain domain. And then I calculate the spectrum, so we can actually stop here, see first the spectrum. There you go. Okay, there you go. You also have it on. You also have it on the slides. Okay, so we can clearly see from the full spectrum, we actually identify the 3 hertz, we actually identify the 10 hertz without problems, but we don't know where they are, right? As we saw before with Miguel. So we want to know now where they are. So what I'll do is to make the window slide. Okay. So actually what you see here on top, this one is the window that I'm sliding. Below you see the signal that is pre-multiplied, and here you see the spectrum. And you see how it widens up. Okay, then we start seeing the second peak here as the window is arriving at this point. We see a lot of ripples, okay, around. That's because this sinusoid finished quite sharply. And then as the last step, we can actually see how the spectrogram looks like. Okay, so here we have a frequency representation. We actually identify quite well that in the range from 1 to 3, we have a frequency of 3 Hertz. This is a logarithmic scale. And then at 10 Hertz, this is in the range 4 to 5, which is what the sinusoid was actually showing. And now what I'll show you is what happens if I change the window. So if I make it sharper, or if I make it wider. So what I'll do now actually is to remove the close all so that we can update and see what goes on, okay? And take a sharper window, for instance, 0.2. Okay, so you see now our window is much sharper. You actually start seeing where the problem might start. We don't see enough cycles of this sinusoid now. So this is making us suspect, and indeed we see it here, that we don't have enough frequency resolution to see it fine. That's because our window is very sharp. Nonetheless, on the other side, this actually were very well localized, just because of its sharpness. Indeed, if we go ahead, you see it now. This is the new spectrogram, and now we see that the definition of the interval is much better, right? Just because our window is much better localized for both cases. What happens now is that this peak is sort of broader, right, with respect to what we saw before. And here we can actually look at that. We can compare the two of them. There you go. This is the other one. You see here the peaks are much better defined. So we see that there is a sort of compromise in between the time definition, the time resolution we have, and the frequency. We cannot have both. Either you use a window that is very well localized, and that will tell you in a nice way, which is a time resolution. So that large part of the wavelet goes outside of the domain. So say, normally when you make analysis like this, you should do the same also for the spectrogram, by the way. You cannot really rely on that part, okay? Let's see how we go with the time. Ah, perfect. So any questions so far on this first part? Yes? Yes, yes, that's true. That's true. That's true. What we can typically see when we use white noise is that the coefficients tend to decay. Sorry, not tend to decay. They tend to spread quite uniformly, but you see some decay around. Okay. So actually, yes, you can see patches, and then say extracting single scales sometimes is hard to do it. Okay. In this case, I think it was quite evident, and indeed, I didn't risk to say anything about what's going on there because actually it's very difficult to tell. There are the patches around here, they're quite well defined and they seem consistent. So I think that they're something that can be safely said. Yes.
I see a very nice lecture. I see that you are using wavelets, cosine, and so on. And there's a good reason to use it because these are the least biased ways of filter for general data. Now you can imagine that you have some data where you have essentially only sawtooth behavior. So it quickly goes up and then it slowly goes down. And for this type of data, one may envision another way of encoding the data. Say just putting a scale and the location of these things. Do you see a way how one can derive, say, more suitable filters for a given data? So this refers to the question which Xavier has asked at some point. No, this is a coding problem or complexity problem of finding something like a good language which compresses the information out of your data. And of course, if you are data specific, there may be other filters which may encode your information much more effectively.
Okay. So the word of wavelet, it's very varied. Okay, and actually that is where the human input enters. I mean, depending on your kind of application, you can find or design following some simple guideline the wavelet that you like the most. Probably in the case you're referring, it would be better to search into some data-driven choice, so not imposing it. Okay, and that's just to avoid what you're saying. That otherwise you put a bias. Okay, so probably it would be better. It will be better to search for something that auto-encodes directly what your data are saying.
So it's a common theme. So when we are talking about physics-based encoder, you can also make a physics-based analysis. So at the moment, you know that your data comes from a certain system of ordinary differential equation and so on. You can already include this knowledge in your physics.
It's a sort of supervised way of seeing the problem. Yes, yes, I agree.
I have a last question. Maybe you mentioned it, but I missed it. Which kind of wavelet, which shape of wavelet did you choose, and how to choose the proper wavelet? Like Mexican hat, all the dB, 1, 2, 3, 4, whatever.
Okay, for this we will need much more lectures. Okay? But this one, I just used the default one of Matlab is the Morse wavelet. Okay, it's the Morse wavelet. Okay. In principle, it depends very much on what you want to do. Typically, wavelets are used, for instance, especially discrete one, for compression of images. And the nice thing is that they preserve edges. Okay, so typically when you blur an image because you want to get rid of the noise, you don't want to blur the edges because it's, let's say you feel much less comfortable, you prefer having noise rather than blurring the edges. In that case, the R wavelet that is sharp is actually doing quite a good job. If you want something that is more continuous, okay, so if you're looking at something that has some continuity, doesn't have spots, like this might be the case, then you go towards like the Morad wavelet, for example, or the Mexican hat. And then I said before, example, if you know that you're searching for Gaussians, that is the case when you have particle images, then you go to the Mexican hat, you don't have doubts. So it really depends on what you're looking at. And then, as Bernd was saying, for some problems, you might want to search into, say, data-driven choices. That's another option. I think it's a beautiful field where you can investigate. Okay. Any other questions thus far? Yes. Yes.
But can you remind what are the properties and interests? I mean, why would you want to have vanishing moments for a wavelet?
And the nice thing of vanishing moments is that it makes it easier to represent smooth stuff, basically, if you want to make it in a very simple way. Okay, so that is what makes those functions interesting. And typically, most applications, when you search for something that's not that aggressive, it requires some smoothness, then looking at functions which have this kind of properties might be useful.
Thank you.
Okay. All right, I think we can move forward. Okay, so we put the ABC of the continuous wavelet transform, but then what happens when you move to the discrete space? And actually, we were working in the discrete space because what I gave in input was a discrete signal, right? Well, in the discrete space, we actually don't need to oversample your signal. Indeed, what we might aim to do is something similar to the discrete Fourier transform, where you go from a base where you have n samples and you have n coefficients. And with wavelet, we might aim to do the same thing. So we want to define a base which has the same dimensionality of our original data. So this is done typically by putting some constraints of our parameters. So while before we let A and B span with certain freedom, what we do in the discrete transform is to build a function in such a way that the scaling and the shifting are, say, linked to integer scaling and integer translations. Okay, so we actually define an A0, which is in most of the cases is 2. So we scale by factor 2 every time, and the translation So say we have binary relations, what I referred before as voices or octaves, and then you have translations, which are again multiples of 2. So if you think about it, you have something like this. So when you select m equal to 1, for instance, then, or say equal to 0, let's go to the lowest level, then this is 1, and what you get is actually the mother wavelet, which is sampling exactly at integer steps. When you go to the next level, so we set m equal to 1, what you're doing is amplifying your wavelet, so you're making, say, let's say you're making it wider, and in that case, since it is wider, it makes no sense to sample at the same interval, so what you do is actually translates by factor of 2. And then you keep going, and what you get is that for the large scales, then you have spacing that goes, say, with the powers of 2 of m. So this is the discrete wavelet transform. I'm putting it there as integral, but actually you can easily write it as a discrete sum. And among this family of wavelets, actually we can select many different wavelets there, but we search for very special ones. And we typically seek for orthogonal wavelets. Why? Because we want to build a basis, right? So we want to move to a different representation where we have, say, n components in that base. So we seek for wavelets which are mutually orthogonal. And the nice thing is that if they span the entire space of the function, so imagine they span L2 of R, you can take whichever function and you can find it as, you can write it as a weighted sum, a linear combination of those wavelets. Okay, so it's just a representation of the base. Okay? So how do you get these families? Well, if you go on the lecture notes, there is a mathematical derivation, and actually it's a very short one. You'd better go to the book of Malat to find a more insightful derivation and more proofs. I want to give you the basic idea, okay? So I'm using an example. How do we build, for instance, the R wavelet? Imagine that we have a signal like this. So this is a generic function in L2, okay? Actually, we can discretize it. So suppose it's a discrete set of measurements. And then suppose that I want to create what is called an approximation at a certain level of resolution. So imagine that you have a sensor which is able to, let's say, average your function over a finite interval. This function, it's a scaling function, what we will call in a moment father wavelet. I can select it, for instance, as a function which has uniform value in each interval n plus 1. So for instance, phi 0, 0 is the function that has constant value between 0 and 1, okay? If I do that, I'm just thinking of a sensor which takes the value of the function here, okay, and put the average value on that interval. So I take an approximation of xt as a bunch of these steps, okay? This one is the approximation at this level. So I'm going away from a moment from the space of L2, I'm going to a space which is defined by this interval function and has approximation of this kind. So it's a space where all functions are sort of stepwise functions. I can do the same trick at another resolution level, a higher resolution one, in which instead of taking these functions, I make the approximation with a function that is, say, narrower. So in this case, a function which is, say, if I take phi 1, 0, it's a function which is equal to 1 only between 0 and 1/2. Okay? Of course, this guy here can be written as two of these guys, okay, one to each other. So in a certain sense, the space of this function is included inside the space of this one. It's nested inside, okay? So these are two different levels of approximation at two scales which are, say, defined as factors of 2, one between each other, just as we were saying before. The curious thing is that if I take the difference in between them, so if I just make f1 minus f2, it looks like a whole bunch of R wavelets. So you see here, this is the R wavelet. So it's like the R wavelet is descending from this choice of the scaling function, the way I'm filtering. And I could actually write the difference in between the two as a linear combination of the R wavelet with interval width equal to 1, okay? So in a certain sense, we get to what Miguel was referring at some point. I could take a function at a certain resolution level, and I could write it as the sum of an approximation at a lower resolution plus some details. This approximation is a linear combination of the scaling function, the phi. This detail can be written as the linear combination of wavelets, okay? And I actually can play the trick also for F1. So imagine that I take this, I go to the next resolution level, so I'm making my scaling function thinner and thinner, and what I get is that this F2 is F1 plus wavelets of smaller interval, 1/2. And I can keep going up to the level of resolution that I want. Ideal, I can go up to the sampling rate of my function. So practically, I can write my function defining a level 0 as the weighted sum of the approximation function. So this guy here depends on where you put your base level, let's say your low-pass filtered version of the signal, plus a whole bunch of wavelets at different resolution levels. These are what are called details. So a bit more formally, but not much more. How do I construct the multi-resolution analysis? That case was for the R wavelet, but I could select whichever scaling function. It doesn't have to be uniform. I can select a different one and get another wavelet. So if I want to create what is called the multi-resolution analysis, what do I need? I need a sequence of subspaces, okay? V0 was the one containing the F0, the function that was constant in intervals of width 1. V1 is the next level resolution, and so on and so forth. I need to select a scaling function called father wavelet. Then I need an equation to write this scaling function in the different subspaces. It's called refinement of two-scale equation. Again, I'm skipping the demonstration. It's just a way to relate all the approximation at all levels as a linear combination of that at the lower level. And then finally, I need the mother wavelet. Again, we saw it in the heuristic way. You can demonstrate that if you want to create a function that is orthogonal to the scaling function, the same resolution, you can play a cheap trick, and you can write it as a function of the coefficients building the scaling function in some way. So I'm skipping the deformation. Just know that this is orthogonal to this. So say practically, this is describing the part that is dropped by the approximation. Okay, so it's the detail that is missing to the approximation. The way this is implemented practically is in a very efficient way using filter banks. And this operation is of order n, so it's very efficient. The idea is the following. Imagine that you have a signal which has a set of n samples, and you want to decompose it at lower levels. So what you can do is to make it pass through a high-pass filter and a low-pass filter. So this H is the high pass, this G is the low pass filter. And then what you do is to take this high pass stuff and you store it somewhere, okay? And when you do it, you don't sample by factor of 2, because actually at the time of filtering, think of the R wavelet. When you filter on a scale, then what you're doing is changing Nyquist in a certain sense. You cannot get details that are smaller than a scaling function. So what you do is throwing this, say, downsampling your signal. This one is what you get after filtering with the scaling function. It's a low-pass filter, okay? So this is your approximation at the next level. If you want to move forward, well, actually already at this stage, what you could do is to write H0 as the sum of the low-pass filtered plus the high-pass filtered. But then you can keep going forward. Now your number of samples has halved, and then what you can do is make it pass again through the same high-pass and low-pass filters. And you obtain a new set of details, which now are shorter. Okay, so imagine that this was 512, for example, this is 256. And the next level approximation, again, you can keep iterating, okay, until you don't get to the lowest level. So this is the way this is implemented. And of course, the choice of filters, Miguel will discuss, I think, this afternoon about that, okay? Or you already mentioned something in this class before. So imagine that you have a signal like this, and you want to decompose using the discrete wavelet transform. Then this is a 4-level discretization. After I make it pass through this set of high and low pass filter, and I store at each step what comes out from the high pass filter, I arrive at the lowest level with what is called the approximation, and then I have the details at all levels. And if you look at the amplitude, you see that they are typically decaying. This is some feature that is normally exploited when you do wavelet filtering. You take the details with less intensity, you throw them out, okay? You chop them from the reconstruction, and you get a signal which contains the most important stuff. If you put all of them together, you see that we moved from a 512 signal, which is this one, to a 512 set of wavelet coefficients, when this is the approximation. And you see, since there is quite some low frequency carrier, we saw it into the approximation, and then you have the details of all levels, and you see that these are actually quite irrelevant. In principle, you can throw them out and clean this signal the same way you will clean it using the Fourier transform. Okay, so to close, let me show the second tutorial. We have actually in the room, I still haven't had the opportunity to shake hands with Nandeng. This test case is from the group of Bernoak, is the fluidic pinball. So you have a set of these 3 cylinders. In this tutorial, we're actually really not interested much in the fluid mechanics, okay? But we are more focused on properties about filtering and compressing using the wavelet transform. So what I'll do is to take the field, put some noise, okay, and start to extract features in some way. Sure. I can send you a presentation if you want. Okay, so this is the original signal. I will not go through the code. It's actually very simple because it uses very compact functions that you find in the Wavelet toolbox in MATLAB, and also in Python there are equivalent functions. So what I do is to take the streamwise velocity and I introduce some noise, right? Very simply some Gaussianly distributed random noise. If I take the first level discretization, so I'm just making the first octave, well, this is done in which way? While for 1D signal, I just needed to filter with the scaling function and get details, and so I obtained a plot of vectors, a plot of data. Well, in this case, I actually need to do it in 2D. So in the end, well, my scaling function, instead of being 1, 1, it will be, say, a square of 1s. And this gives a low-pass filtered version of your signal. This is done, by the way, with the R wavelet. And at the lowest level instead, well, I have several options for the wavelet. One is a function combining, say, psi for the x direction and psi for the y direction. So it's sort of, say, diagonal detail. Another one is psi for the horizontal details times phi, and that is still orthogonal to this. So it's nice to isolate horizontal details, and I can do the same for the vertical details, okay? So I need to find, say, to seek, in this case, the 3 opportunities I have to build functions that are orthogonal to the approximation function, and so that allow to obtain all the details that are missing when I filter out here. If I go to the second level, so what I'm doing is taking the approximation, what you found in this first square up here, and say further filter. So now I have the details at the second level, and you see that while this was noise dominated, I start seeing here some features, some horizontal edges that are those coming out from the shear layers here, okay? Notice that here what I did, if you look in MATLAB code, I actually rescaled all these so that they are at 8-bit levels, but actually these details are much weaker than what you find here. So in principle, what you can do is to make a decomposition and throw out the stuff that is irrelevant. So this is what you get. And actually, I think here it probably makes sense to open quickly the MATLAB code. Let's quit debugging here. So this is where I put the noise. This is the decomposition I used just for purposes of demonstration. And then later, what I do is to use a 4th-order Dobeschi wavelet to create a 4-level discretization. So how do I perform the thresholding to get rid of the noise? Well, what I do is to sort the absolute value of the coefficients, okay? And then decide which is the fraction to maintain. This is actually a tough decision. In this case, I just put a number, but in principle, this decision is normally taken considering the amount of noise you estimate in your signal. There are many ways of doing it. There is the universal scaling. There are interesting papers from Johnson in the 90s. So there are ways to make this selection in a wiser way that I did, okay? But anyway, let's live with the 2% being fine. And then what I do is just to maintain the largest coefficients, okay? So let's go back here. There you go. So indeed, after filtering with Wavelet, I see that I retain most of the features, actually make a quiet job in cleaning. And what I'm putting here is what I get if I use a standard filter in the Fourier domain by retaining the same amount of coefficients, so the same 2%. This doesn't have to be necessarily fair, okay? Maybe in the Fourier domain, I might need less coefficient. And actually, this is one of the cases where the features are quite smooth, and Fourier normally does a good job. Nonetheless, here you see that there are some residual of the noise, so I might be more aggressive here, which might mean that I might lose some more feature of my signal. So with this, I conclude. I hope I gave you at least the basic idea that is needed for this afternoon to work with filter banks and wavelets and try to understand what is behind the multi-resolution POD, and let's see if you find some interesting application in your future to use wavelets. And now we have some time for questions, so please go ahead. Where do you see the wavelets in 20 years?
Something like that. So, for instance, for the cylinder work, you could use, at the moment you are doing a Fourier transform, you assume something like you have a ergodic behavior. So you are going back to your original data point at some periods.
Yes, and that's what you see.
And if this is the case, so this is classical example for ergodic behavior. So at this point, you should not throw away the past data. To some extent, the past data can be used to reconstruct this and set a bias to your filter to being closer to what you have recorded in the past.
Yeah,
and you have, are now presenting tools which you can use if you don't have this ergodicity.
I agree.
And would you have an idea where you could make the switch? So you look at the data and do you have an idea where you can push this switch to say if you are, should use your past data, or where you have something new and you need more generic tools for the filtering?
I actually haven't thought about it. As an experimentalist, I don't used to have time resolution in my PIV measurements, so I really can't use easily the information I have before. Okay. Especially low Reynolds number, high Reynolds number, you don't have that thing available. In principle, when you do, yes, it might make good sense to use that time information. Normally in experiment, what we do is just to apply Fourier also in time. So you say you combine time and space. That is the dummiest thing you can do, but normally works quite well when you have random noise. But then I agree, you can build, say, better tools to do this scale-wise. So say sort of enforcing also the persistency of scale if you want to track down the stuff that is active and the stuff that is not. Yeah.
If you really believe in ergodicity, you can take the POD and essentially use an autoencoder.
Yes.
From the data, do POD, and then you have the same results. And
I think this guy is going to, we are spoiling Andrea. Okay. This guy is going to talk about this afternoon, but yes.
The next thing, the autoencoder uses all the data. You can also use the temporal coherency. And then you have a second layer. So you have to do these things for the online extraction of a phase from flow visualization. So if you want to do control based on flow visualization, you have to use both type of
this is a very nice idea, actually. Yeah. Thank you.
Are there any other questions? Well, then if not, we thank again Professor Discetti for this excellent introduction.
Okay.